there's me. Okay, so let's go ahead and do something with that image. For example, let's edge detect that image. Percent always means the most recent thing we got. So there's the edge detection of that image, or let's say we make a morphological graph from that image. So now we'll make some kind of network. Oh, that's quite impressionistic. Okay. Or let's say we can make something. Let's try and make something here that kind of controls, sort of automatically make a little user interface here that controls kind of the degree of edginess that we have here. So there I am, and now we can adjust this, and we'll make things change there. Well, maybe we can get let's do something different here. Let's get just a table of all of those bunch of results from different levels of edginess in that picture. Okay, so there we go. And now, for example, we can say, let's take all of those images and stack them up and make a 3D image. So there we have that. And now we can move around here. Oh, somewhere there I am. Planets. For example, I could now say, give me an image of each of those entities. So now I'll get some images of planets there. For example, I could now say, if I wanted to, I could say, take, it knows all sorts of things. So let's say we could ask it, what are the masses of those planets? Okay, there are the masses of the planets. Now we could, for example, make a little infographic showing all the various planets arranged so that they are of a size corresponding to their mass. So I think it's fairly amazing that we can use just that tiny amount of code to make something like this. But let's go on a bit. Let's see, for example, let's see where the internet thinks that my computer is right now. We could, for example, say, when's sunset going to be at this position on this day? Or, for example, we could say, take sunset time minus now. That's 8.3 hours from now. Or we could get, let's say, a map of, let's try and get something like a map of 10 miles around the center of Austin here. So let's do that. So now we're using data about maps. Or let's say, for example, that we want to get a whole series of maps. Let's do something where we say, let's do powers of 10 kind of regions around here. Let's find my mouse. There we go. So now this is going to make a series of maps going out from Austin to, actually by this point we're covering almost the whole world around Austin, other than that little spot in the Indian Ocean there. Or we could, for example, let's say we go, let's go off planet, for example. Let's say we do the same kind of thing for, we ask for the Apollo 11 landing site, and let's show 1,000 miles around the Apollo 11 landing site on the moon. Do all kinds of things. Let's say we want to, let's try something in a different kind of domain. Let's get a list of Van Gogh's artworks, another kind of thing that we would know about. And let's say we want to, let's take, let's say the first 20 of those, and let's get images of those. It'll take a little while. Let's see, here we go. So there are some images, and now we can, for example, we can say, take those images, and now we can say, okay, what are the dominant colors that were used in those images? So I have to do a little bit of computation here, and maybe we can go ahead and say, let's plot those colors in a chromaticity diagram in 3D. So we get the result. So this is kind of showing us what the distribution of colors in those particular pictures is. So X is X. It's symbolic. And the point is that basically anything can be represented like this. Something like, if I type in Jupiter, it's just a symbolic thing. Or, for example, if I were to put in an image here, It's just a symbolic thing. And, or for example, I could say, I could ask about, I could have something like a slider, a user interface element. Again, it's just a symbolic thing. And now when you compute, you can sort of do anything with anything. So you could like do math with X, or you could do math with an image of Jupiter here, or you could like do math with a slider here, or whatever. So it's taken me a really long time, actually, to understand just how powerful this idea of symbolic programming really is. Every few years, I understand it a little bit more. Long ago, we understood how to represent programs symbolically and documents and interfaces so that they all become sort of instantly computable with. Recently, one of the big breakthroughs has been understanding how to represent not only operations and content symbolically, but also their deployments. Okay, so there's one thing I need to explain first. What I've been showing you here today has mostly been using a desktop version of the Wolfram language, though it's going to the cloud to get things from our knowledge base and so on. Well, with great effort, we've also built a full version of the whole language in the cloud. So let me use that interface here, just through a web browser. So I can just go, let's see. Let's go here. Okay, so now I'm going to have the exact same experience, so to speak. Let's just check things are working. Okay, that's a good sign. You know, we can type whatever we type. We can do all these same kinds of things purely in the cloud, just through a web browser. You know, actually, in my 40 years of writing software, I don't believe there's ever been a development environment that is as crazy as the web and the cloud. And it's taken us a huge amount of effort to kind of hack through the jungle to get the functionality that we want. We're pretty much there now. And of course, the great news for people who just use what we've built is that they don't have to hack through the jungle themselves because we've already done that. So we can let me run this piece of code, and this will create. It will deploy something to the cloud. The thing it deploys to the cloud is something that will run, will create a form and then run that little piece of code here. The form will say it's going to have a field that asks for a cat, and it's going to look for a cat breed. Let's run that form here. So now we can type in, let's say, Siamese, and it will go back and run that code, hopefully. It's very surprising. It should be very fast. Okay. Well, there's a picture of a cat. Let's for example, let's go back here and make that code a little bit more elaborate. Let's just add another field here. Again, we deploy to the cloud, and now we should get something where we have, you know, something like this. We have a cat, and we hopefully have a cat as an angle there. And so now we can, that was making sort of a little web app, which we can also deploy on mobile and so on. We can also make an API if we want to, so let's try doing that. Let's do the same, let's use the same piece of code. Actually, the easiest thing to do would be just to edit that piece of code there and change this from being a form to being an API. And now the thing that we have will be an API that we can go and fill in parameters to. We can say cat equals Manx, you know, angle equals 300 or something, and now we can run that, and there's another cat at an angle. Actually, we can go ahead and take what we have here. So that was an API that we just created that could be used by anybody in the cloud. We could say, if we wanted to, we could ask to create embed code for this, so that we can run it, let's say, inside Java, and here's now the code for calling that API from inside a Java program, so that you can sort of effectively knit Wolfram language functionality right into any project that you're doing in any language. It's sort of really critical that the Wolfram language can represent different types of data in a standard way, because that means you can immediately do computations, combine data bins, whatever. I have to say that just being able to sort of throw data into this Wolfram data drop is really convenient. Like, of course, we're throwing data from the PyDay website into a data bin, and that means that we can, for example, it's just one line of code. Yeah, if I can get back. It's just one line of code to go and be able to work out where in the world people have been interested in Pi and generating Pi t-shirts from, and so on. You might know that I've long been an enthusiast of personal analytics. In fact, somewhat to my surprise, I think I'm the human who's collected more data on themselves than anyone else. So, for example, here's a dot for every piece of outgoing email that I've sent in the past quarter century. Now with our data drop, I'm starting to accumulate even more data. I think I'm already in the double digits in terms of number of data bins. Like, for example, here's one. Let's see if I can pull this up. This should be a data bin from the my heart rate during Pi Day, which I figured out what was happening at different stages in the day there. I don't think there's no huge peak right at the Pi moment of the century, unfortunately. Okay, with all this data coming in, what are we supposed to do with it? Well, within the Wolfram language, we've got all this visualization and analysis capability. One of our goals is to be able to do the best data science automatically without needing to take sort of data scientists' time to do it. And one area where we've been working on that a lot is in machine learning. So let's say you want to classify pictures into ones that are, let's say, classify, let's say we want to classify pictures that are going to be day versus night pictures. Let's see if I can pull that one up. That's not good. It's hard to type again. There we go. Okay, so here I've got a little tiny training set of pictures corresponding to scenes that are day or night. And I just have one little function in the Wolfram language, classify, which is going to build a classifier to determine whether a picture is a day or a night picture. So there I've got the classifier. Now I can just apply that classifier to a collection of pictures, and now it will tell me, according to that classifier, are those pictures day or night? So the way this is working, we're kind of automatically figuring out what type of machine learning to use, so that it is just one function to do this. We've got lots of built-in classifiers as well, like you can, all sorts of different kinds of things. Let me show you a new thing that's just coming together now, which is image identification. And I'm going to live dangerously and try and do a live demo of some very new technology. And actually, I realize I asked somebody to go to Walmart and buy a random pile of stuff to try for image identification. So this is probably going to be really horrifying. Let's see what happens here. Let's first of all, let's set it up so that I can actually capture some images. Okay. I'm going to give it a bit of a better chance by having it not have too funky a background. All right, let us try one banana. Let's try capturing a banana. And let us see what happens if I say image identify. In our language, that thing. Usually it's very fast. This is a bad sign. Okay, that's good. We have to try a couple of other things. Let us try, what is that? That appears to be a, let's see what it thinks this is. Okay, let's see what that comes out as. I've got okay, let's try one more. How about this? Let's see. I think to give it the best chance, let's try doing that. Okay. Let's try image identifying that thing. Okay. So oh, wow. Okay. I knew something. It says it's an African violet. That's pretty cool. Okay, so actually, this does amazingly well most of the time. And what to me is the most interesting, we can go and try it on other things too, but the most interesting thing to me is that when it makes mistakes, like with the Triceratops, the mistakes are really very human-like. I mean, they're kind of mistakes that a person might plausibly make. And actually, I think what's going on here is pretty exciting. You know, 35 years ago, I wanted to figure out, you know, how brain-like things, and I was studying neural nets and so on. I did all kinds of computer experiments, and I ended up simplifying the underlying rules that I looked at, and wound up studying not neural nets, but things called cellular automata, which are kind of like the simplest possible programs. And what I discovered is that if you look at that, in that sort of computational universe of programs, there's a whole zoo of possible behaviors that you see. So, for example, here's an example of just a bunch of different cellular automata. Each one is a different program showing different kinds of behavior. Even when the programs are incredibly simple, there can be incredibly complex behavior. Like, there's an example. You can go and see what it does. And that discovery kind of led me on this path to developing a whole new kind of science that I wrote a big book about a number of years ago, that's ended up having applications all over the place. And for example, over the last decade, it's been pretty neat to see that the idea of modeling things using programs has been winning out over the idea that sort of dominated exact science for about 300 years of modeling things using mathematical equations. And what's also been really neat to see is the extent to which we can discover new technology just by kind of mining this computational universe of simple programs.